Hi, how's it going? My name's Corey, and this is my capstone project presentation for CS220, which is computer architecture and assembly language. For this project, I decided to research basic assembly language, otherwise known as BAL. This language came to be in the 1960s, back before home computers were actually a thing. I thought this is an interesting topic to research because there's not a lot of information available online for this language, and it's just an interesting part of our past as programmers. Something that we've definitely moved on from since then, but you can still see portions of this particular language working in modern languages, so it's pretty cool. Um, so to start with, this is an era of punch cards. Basically each card had 80 columns on it, and each column or range of columns, say from like 29 to 37, were specifically used for one thing or another. So each column had its purpose. For instance, the first column, if I remember correctly, was for mnemonics. So that would be where your variables were. This language can handle multi-letter mnemonics, which is pretty cool. Before this, apparently it was just single letter mnemonics, which would be a nightmare to work with because you'd just be looking at letters like A, B, C, and trying to just assume what they mean and hope that someone had documented it. But anyways, moving on. So these punch cards had 80 columns. Humans would punch the holes in the cards, and then they'd feed that card into a machine to see if it had been punched correctly. They had ways to, like, they'd feed it in, and then the holes would be detected by pins, and if the right holes were punched, then it would be allowed through the machine. Otherwise, it would be rejected and punched on the edge of the card so that they know it was a rejected card. And then obviously we'd compute data based on what was punched in these cards. So any number of things could be punched in. This is essentially the program, this punch card here. This is taken directly from the manual for the IBM System 360, which is what this language runs on, or what it initially ran on. So that's pretty cool. This is an actual part of history from like 60 years ago. So anyways, they punch the cards, they compute what's based on based on what's in the cards, and this card is essentially the program. So it's a very physical programming process. Like I said before, cards were made by punching holes, and then pens would kind of determine if the holes were punched or not while being fed through a machine. There's 80 slots, and it was primarily used for accounting. So back then, the major problem that computer systems were trying to solve was accounting, finance. It's basically a nightmare to go through thousands and thousands of sales records. So this is largely used to track sales in companies. And it's very useful for that. From what I remember looking up in the manual, this process could handle about 20,000 of those 80 slot cards in 34 minutes, which is an insane number for the time, considering people were still sorting everything by hand, doing everything by hand manually, physically writing, tracking things. So that would have been a nightmare to keep up with, and no human could do 20,000 records in half an hour, So this is pretty miraculous invention when you think about it that way. So the purpose is for sorting data. So IBM made this specifically so that we could take a whole bunch of sales records and split them into a bunch of different bins. And then those bins could later be sorted even further if desired, or they could then be taken in for record keeping or creating reports, which was one of the biggest uses for this thing. Creating reports, often grouped by like customer number, sales number, or product number. This way they could start kind of tracking like, okay, what is what is selling good, who is selling good, who isn't selling things very well, and stuff like that. And they could actually start to compile this data in shorter amounts of time and then act on the information much faster than they could have in the past. I mean, 20,000 cards for a single person, I have to imagine would have been at least a week's worth of work. And then it's just boiled down to 30 minutes. So it's very amazing. Also, they could find sales trends with this. So, I mean, the possibilities are kind of limitless with that. Like, as long as you know how to spot the patterns, you can kind of set the system up to find those patterns if desired. And then IBM made this programming language to sort of bring uniformity to computer systems. And up until this point, like in the 1940s, 1950s, there were a lot of different people um, creating their own assembler languages and their own computer architectures. And so there was 100 different ways to do it, and everyone was doing it a different way, which is kind of a nightmare if your company needed to, um, let's say, change out one set of computers somewhere. Um, they would have to change everything. Everything would have to work together, and nothing was backwards compatible. So another big part of this was compatibility across lines and the ability to, if desired, just change out one machine and the whole system could keep working. It wouldn't cost thousands of dollars to switch. So those are the big reasons for this language to exist. How is it sorted? So this is the IBM 82 sorter here. This is another picture taken directly from this process. So you can see we've got 13 slots here. There's 12 slots for particular organization, and that can be set up however the user desires. If you had 12 employees, or if you had 12 different product lines or something, that could be how it's sorted. And then the 13th sorting pile is for rejected cards. So if we find an expected, this is like one of the first branching statements, essentially, is this machine, is this physical machine. So if a hole punch is the expected result, then it's going to go into the expected pocket, right? Otherwise, else, we're going to place the card into the rejected pocket. And so, I mean, that's the first branching statement right there, just massive physical machine. It's pretty cool. So this thing could take in, like I said before, thousands of card inputs per hour. It's automatically sorting for these holes that have been punched by scraping pins across and seeing, okay, the hole is there, it's there, okay, that makes sense. This one goes into this slot. And then it would just continue on like that until all the cards are sorted. So that's pretty cool. The sorting was very powerful. It's basically, I mean, you could arrange it by anything. I have a few examples here, like employee number, male or female, marital status, whatever it is. As long as the person can set it up and it's ready on the form, it's part of the form, the 80 columns, then we can sort it. And it's a very powerful feature. There's also comparison sorts. So, you could have greater than, less than, equal to, all that kind of stuff was available. And then for the future, obviously, eventually basic assembly language, or BAL, ends up being able to run on a computer. So that's the future. Obviously, in the 60s, we didn't have home computers or screens. We didn't have mouse and keyboard and stuff. Well, we did have a keyboard, to be fair, but we didn't have any kind of electronic device that it was hooked up to necessarily. This was much more manual back then. But eventually we got it onto computers. It could run on the system 3860, which is one of the first like modern computer architectures. Had like a CPU, it had input output, it had the ability to display to or write to a screen. And these were all like built-in functions. We can kind of see here, this is an example of some code from an educational source. This is a PhD here, Peter Marr. I'm not sure if I'm saying his name correctly, but want to make sure to credit him for writing this. and it's pretty cool. So you start off with a program name and the C sect, which I guess tells the program like this is the beginning. So start reading from here. Um, and then you can see the first column is for mnemonics. And this system here, it follows the 80 column punch card uh, conventions. And so that's why oftentimes when you see basic assembly language, you'll see that everything runs down the same column. And this is important because the program is expecting mnemonics, for example, to be in the first column. And so if these aren't here, then they won't be treated like variables, essentially. They won't be able to be called on or remembered. Um, Probably the program won't even run. So, um, and then we have a few examples here. So, save registers, we're basically preparing these registers to be used 14, 12, and then 12, 13. So from what I can understand, this means 1 through 12. And I don't understand why he puts it like this exactly. That would probably take a bit more research into basic assembly. Um, but what I do understand is this is essentially like 1 through 12. And yeah, so those registers will be available as like one register or one array of registers. Um, what else? Some break down some of these things. Okay, so here we're linking save area for IO operations. So we have an actual variable named mySave. And then 13 is a place in memory. Um, and these two things are like parameters being sent into the save function. So you can see like all the mnemonics essentially are expecting some sort of argument to be sent back. And based on that argument, we get different results. So another example here is like C is compare. And when you see like C2 comma equals F1000, what this is saying is we're comparing to see if this loop is ended. And if it has, then we're going to continue past this line of code. If it hasn't, then we're just going to go right back to the beginning of the loop again. Okay, so I mean, it's pretty similar to Jack. I mean, I'm sure people looking at this can kind of see some similarities. Um, I will say that this program can actually handle more than Jack can. This program has mathematical functions built in for decimal points and exponential numbers, which is pretty cool. And if you actually look in the manual, like on the back side of this, there's for their addition, there's 3 different addition functions, one for normal numbers, one for decimal numbers, and one for exponential numbers. So they all have to be treated differently. But at the end, the correct number is spit out. So, the user doesn't know that's happening behind the scenes, but I just found that interesting. So they can handle all kinds of different math. This thing had branching statements. It has labels, as you can see, L1, prime, P loop, like those are things to go back to if we're branching or looping. And this programming language actually dominated the market for years. I believe by 1989, IBM's computer systems, this uniform backwards compatible setup that they had, by 1989 was 50% of the world's computer market, which is insane. And we can essentially consider this to be the birthplace of object-oriented programming because this program was replaced by COBOL. And COBOL in 2002 or 2006 eventually went from a procedural programming language to an object-oriented programming language, or at least the ability to have objects. And this was a direct predecessor to basic assembly language. So as you can see, I mean, the future was pretty bright, and this program or programming language was the birthplace for a lot of the modern architectures that we see today. So that concludes my presentation. I hope that you enjoyed listening and learned something new about this. I had a fun time researching it. It was very difficult to find info online, uh, but what I did find was enlightening, and I can see just how far we've come from that physical process to this, uh, much more digital process. So thank you for watching, and I hope you have a good day.